And our next speaker, Niklas, is going to tell us about salvation by the compiler, which in this building seems like an appropriate title.
Thank you. So I'm happy to tell you how compilers can bring security guarantees to unsafe languages and present how we can verify that. My name is Niklas Mück, and this is joint work with Aïna, Linn, George, Dreyer, Deepak, Garg, and Sammler. So let me start with an example. Here we have a program that allocates two local variables, x and private. It then passes a pointer to x to an I/O library in order to read an input. And afterwards it asserts that the private variable did not change. The interesting thing about this program is that this library is untrusted. Imagine that it is some library that a programmer of this program has taken from the internet without inspecting the source code. So we know nothing about this I/O read library, and it could even be maliciously crafted. And we are at POPL, so we would like to verify this program. Concretely, we want to verify that this program has no failing asserts. But what does this even mean? I mean, there's this library call we know nothing about. So the best thing we can do is to quantify over all possible implementations of I/O read, and then study our program when linked together with such an arbitrary implementation. This property is a well-known security criteria called robust safety, and will be the attacker model for the rest of this talk. So we'd like to verify the robust safety of this program, but does this property even hold? This depends on the programming language the program is written in. And I have bad news for you, this program is written in C. And the program is not robustly safe in C. To see why, let's consider an example implementation of I/O read that attacks the program. It takes the pointer to x, then subtracts 1 from it, and tries to store 0 to the address aligned next to x. And in fact, if we compile this program with GCC, the assert fails. The reason for that is that this out-of-bounds access here is undefined behavior, which means that the compiler is allowed to do anything. GCC exploits this by aligning the two variables x and private next to each other in memory without any protection mechanism. So as soon as an attacker is able to trigger undefined behavior, there are no guarantees according to the C standard, so this program is not robustly safe in C. Does this mean we are out of hope? Well, I said a compiler can do anything. This also means that a compiler can choose to make the program robustly safe. Compilers, such compilers that introduce security mechanisms are called hardening compilers. So even though a program is not robustly safe in C, the compiler can choose to harden the program such that the compiled program is robustly safe. Let's see what this means to our example program from the beginning. We want to build a compiler that can harden the program such that the compiled program is robustly safe. At first, the bottom line there might look like the robust safety property from the beginning that we said does not hold. But note that we have the compiled program there that is not linked with an arbitrary C library, but with an arbitrary low-level context. And I would say this is the actual property we care about, because in the end we never execute C directly, but we always execute a compiled program. So does this sound good? You probably wonder how a compiler can achieve something like this. And in fact, there are many ways. But we focus on hardening compilation via compilation to capability machines. Capability machines are a special kind of CPUs that perform dynamic security checks at runtime. So let me explain the key idea. The problem with standard assembly is that a pointer is just an integer, the address, from which the aligned address can be computed from and then accessed. On a capability machine, however, a pointer is a capability, and such a capability is needed in order to access memory. A capability is such a tuple that does not only consist of the current address, which we have in orange, but also has a permission tied to it, for example, read-write permission, and more importantly, it also has bounds. And, well, the hardware then checks that you have the right permission and that you only access memory within the bounds. So let's consider the attack from before again, that adds -1 to an address and then tries to store 0 to it. If we now give this attacker only a capability with bounds for x, then this attack is detected by the capability machine as illegal and prevented at runtime. And the compiler can make use out of this. If a compiler compiles local variables to capabilities with disjoint bounds, it can rely on the capability safety of the hardware. So now you hopefully have a rough idea of how one can build such a hardening compiler. The big question we studied in this project is how to verify such a hardening compiler. And in fact, we are the first one to study the verification of these kind of hardening compilers for robust safety. And that's why we needed to understand a more fundamental question first. What does it even mean for a hardening compiler to be correct? And as we will see shortly in this talk, this is by far not obvious. To answer this question, we develop a formal correctness criteria and specify hardening compilers using a separation logic. Then we develop a new proof technique to prove the soundness of the logic end-to-end for the compiled program. We also demonstrate our method by verifying a simple hardening compiler from a source language rec, which is a simple C-like toy language with undefined behavior, to a target language cap, which is an idealized assembly language with capabilities. And all our work is formalized in ROC. So when approaching a new research question, a good first step is to study the literature. And in fact, there's a related problem studied in literature called robust safety preservation. Preservation in the sense that it's a property about a compiler that compiles programs written in a secure source language that are robustly safe, such that all programs that are robustly safe in the source language also need to be robustly safe after compilation. So robust safety needs to be preserved. In other words, a malicious low-level context should not have any extra power to break safety. You can see that this looks quite similar to our problem, since the goal is the same. However, in our setting, there's nothing to be preserved, since the source language, our source language, is not secure, and hence the source program cannot be robustly safe. So the goal, robust safety of the compiled program, is clear, but a question for even specifying a hardening compiler is what programs can a hardening compiler make robustly safe? I mean, clearly our motivating example from the beginning should be made robustly safe by the compiler, but not all programs can be made robustly safe. If a program, for example, deliberately shares its private variables, then there's nothing meaningful a compiler can do about this. Once a pointer is shared, we lose its integrity. So what program should a hardening compiler make robustly safe? Well, I mean, intuitively that's somewhat clear. All programs that would be robustly safe if C would be a safe language. But the question is, how can we formalize this intuition? Our idea is to use a program logic to characterize all programs that should be robustly safe, should be made robustly safe by a hardening compiler. Concretely, we propose a logic reckon, which is a separation logic built on Iris and inspired by OCPL. Reckon tracks what pointers have been shared with untrusted code. So a pointer can either be exclusively owned by a program or shared with untrusted code. For the first part, we use the standard separation logic points to that expresses ownership of a location, or exclusive ownership of a location, together with the information that this location currently stores some value B. Reckon then additionally comes with a low integrity points to that expresses that some location has been shared with untrusted code and that the value stored at this location is unknown because untrusted code can have changed it. When you have such an exclusive points to on the left, you can trade it in for a shared points to, but there's no way of transitioning back. Because as soon as you pass a pointer to untrusted code can remember this pointer by storing it in their local state. And then Reckon comes with one central rule, which is this rule here, that allows you to call arbitrary unsafe functions. This rule says that you can execute arbitrary untrusted code as long as all arguments that you pass, all pointers that you pass are low. But let's take a look at an example of Reckon in action. On the left, we have our example from before, and on the right, we have the 3 key ingredients of Reckon that I just showed you. In the beginning, we start with a trivial precondition and then allocate x. This gives us the exclusive knowledge that x stores the value 0. Similarly, allocating private gives us the exclusive knowledge that private currently stores 42. Next in the program, we have this call to an untrusted function. For that, we would like to use the rule that Reckon provides, but in order to use the rule, we need a low points to for the argument. So we use this one-way transition, trade in our exclusive points to for x, and get a low integrity points to. With that, we can use the rule and then frame around the private points to for, or the exclusive points to for the private variable around this function call, such that afterwards we still know that private stores 42 and this assert succeeds. So this is Reckon, and with that we can answer the question of what programs a hardening compiler should make robustly safe. All programs that are intuitively robustly safe, which we formalize using a program logic. So the answer is all programs that can be verified in Reckon. And with that, we found an answer to the first question that I listed as our contribution. We found a formal correctness criteria for hardening compilers. The big open question is, how can we verify it? And effectively, this reduces to the soundness of the logic. But the key rule of the logic is not sound if the untrusted function is implemented in the C-like source language. I mean, that's the reason why we needed a hardening compiler in the first place. So the soundness statement that we prove is this end-to-end result, that our logic Reckon is sound if you compile the program with this hardening compiler, and then the compiled program is robustly safe. We factor the soundness proof into 2 steps. The first step is to prove the soundness of all the normal rules like load and store and similar. There we follow the standard approach of proving the soundness of these rules against the source language and then proving compiler correctness so that the compiled program refines the source program and therefore also fulfills these rules. So this first step is non-trivial, but does not require any fundamentally new technology. However, the second step is to show that arbitrary untrusted functions follow this rule and can be safely executed if all argument pointers are low. Note that this rule more importantly says that low points tos for all arguments are enough to execute untrusted code safely, and that all other exclusive points tos can be framed around and are preserved by untrusted code. Now the problem here is that we need to prove this rule for all low-level contexts, but the rule is stated in a program logic for the source language, so we have different languages there. Again, we want to take inspiration from the literature. The standard approach to reason about programs that interact with untrusted low-level code is a technique called backtranslation. The idea is to, given a low-level context, construct a source context that does the same attack. If the source language is now secure, then the source program is robustly safe against this constructed context. And with that, because this low-level context performs the same attack, one also knows that the compiled program is robustly safe against this low-level context. However, constructing the syntactic back translation explicitly is painful and unfortunately not even enough in our setting, where the source language is unsafe. One would additionally need to prove that all constructed programs fulfill the rule of the program logic, which is not obvious since arbitrary source contexts do not fulfill this rule. That's why we develop a new semantic proof technique. The idea is to leave the syntax behind, since on the semantic level, we can easily characterize all programs that fulfill the rule. We do this by defining a semantic source context that we call sim, and then show that sim over-approximates all low-level contexts by a new proof technique that we call semantic back translation. For convenience, we already moved to the semantic domain at the target level and define a universal contract that semantically over-approximates all possible low-level contexts. Then, semantic back translation does not need to worry about syntax at all, and we only need to show that sim simulates unif. The key part of this approach is how we define this unif and sim. And I want to use the rest of this talk to give you an idea of how we define them. We define them using DIMSUM. DIMSUM is a multi-language semantics framework developed by Sammler et al. It was originally developed for compositional compiler correctness. In DIMSUM, programs are given as semantics as label transition systems with call and return events for the source language and jump events for the target language. For example, our running example from the beginning becomes this transition system here that has call events with the current call and return events with the current global heap attached to the event, and all other operation becomes silent tau events. In this setting, we can now define unif and sim as non-deterministic transition systems that non-deterministically perform all possible attacks at the same time. And the cool thing is that we can define sim such that it by definition has the key property we want it to have. We can define sim such that it directly fulfills the rule of the program logic. For this, we use a very handy feature of DIMSUM. Namely, DIMSUM allows to define non-deterministic transition systems with separation logic side conditions. We use this feature for a new purpose to define a transition system that implements an axiom of a program logic by definition. So the trick is to define sim to listen to all call events and then emit return events and put a pre and post condition as a separation logic side condition. Concretely, sim listens to all incoming calls such that the precondition of the HOR rule, together with a separation logic frame, holds at a current state interpretation for the current heap. For the outgoing event, we put a post condition of the HOR triple as a side condition. Then sim non-deterministically performs any attack such that any attack to the heap, such that the post condition is satisfied on this heap. Technically, we require that the state interpretation needs to be updated to this new heap while preserving the separation logic frame. You can see that this way we can define sim just to be strong enough for the soundness of the program logic, which minimizes our back translation effort. And on my final slide, I want to give you an idea on how this semantic back translation proof looks. Ultimately, we want to show that arbitrary untrusted low-level code is simulated by sim. One instance of this untrusted code could, for example, be this transition system. We first over-approximate this by a non-deterministic transition system that does all attacks at the same time. So maybe the second branch of this transition system could be the concrete instance of the untrusted code we have on the left. We saw how we define sim as a transition system with separation logic side conditions. Here, we additionally wrap it in a so-called wrapper that we inherit from DIMSUM. The wrapper translates between source and target events such that we can then relate sim to the untrusted low-level code. And then we need to prove that unif refines sim. Here, the trick is to define unif in the same shape as sim. So also as a non-deterministic transition system with separation logic side conditions. For that, we define a low predicate for target values and assert that all values in the registers are low. Then, semantic backtranslation, in a sense, boils down to translating between the low predicate of the source and target language, and is surprisingly easy after all. The paper goes into a little more detail, but this is the basic idea. And with that, I want to summarize. We prove robust safety for an unsafe language that is established by a hardening compiler. As a characterization criteria, we propose to use a program logic with this simple rule that characterizes the guarantee that the compiler gives independently of the concrete implementation. As a proof technique, we propose a novel technique that we call semantic backtranslation to prove the soundness of the program logic end-to-end for the compiled code. Thank you.
We have a few minutes for questions.
Hello, thanks for the talk. There was a slide where you said Reckon does not have step indexing. Could you say a bit more about that, and what is the reason?
Yes, that's basically a limitation we inherit from dim sum. Yeah, we don't have step indexing because yeah, basically the technical reason is you saw. On this slide, we have the satisfiable predicate, and there we basically assert that the separation logic proposition is satisfiable at the step index 0, and therefore we don't have step indexing in this logic.
Okay, so thanks for this talk. I was wondering, can you go maybe to the next slide so it's clear to everybody?
Yes.
So yeah, this unif in blue
Yes.
over approximate arbitrary target context.
That's
and you
true.
create a single red sim, right, for
Yes.
this unif. So, I mean, if you have some familiarity with that work, you were talking about the preservation of robust safety. This means you are creating, there is one single source context that kind of works for arbitrary target context. So I suspect that you have much stronger properties than robust safety. But we can take this offline and maybe if you didn't look into it.
Yes, so in this work we only target robust safety.
Yeah.
But yeah, it's future work to find out what exactly we get there.
Okay.
Yeah,
Thanks.
it depends a little bit on how you exactly define unif and sim.
Thank you.
Hi, thanks for the talk. This is really interesting. I think you mentioned that there are some programs which can't be made robustly safe.
Yes.
The example you gave was sort of degenerate. Are there like useful programs that can't be made robustly safe?
Useful programs that can't be robustly safe. I haven't really thought about this. I mean, as soon as a program shares pointers with untrusted code, it basically gave up all invariants it has on these particular pointers. So I don't know. So in order to be robustly safe, programs need to be aware of that and, well, like, don't share pointers where they have invariants on with untrusted code.
Hello. Hello. Oh, so when you're compiling the low-level code, I mean, you do have to have a C compiler that is compiling the untrusted code, and then you have to actually have some kind of capability protections or something like this that actually implements that behavior of hardening that you describe. I mean, basically this presentation seemed to be about the separation logic side of things, but at some point you actually have to implement this behavior in the compiler. Like what is the compiler doing?
Okay, yeah, first of all I need to clarify, we don't compile the untrusted code. We only compile the program we reason about, and then the program can be linked with any arbitrary untrusted low-level code that can either be compiled or it can be a maliciously crafted low-level binary. Yes, but what does the compiler do? I mean, clearly we built a simple toy compiler in this project that basically does what I said in the beginning. It compiles local variables to capabilities with disjoint bounds, and then makes sure if a program passes a pointer to untrusted code, then the compiled program only passes like a capability with bounds only to this local variable.
So are you relying on hardware protections in order to do
stop
this?
here and take the rest of the conversation offline so that we can move to the business meeting.
Thank you.
Thank you very much.